I'm back. All right. I got my internet's acting up, so I'm having to run off hotspot off my my cell phone. Okay, where was I? I was talking about this one here. Can everybody hear me okay? Okay, well, let us continue. All right, so we were talking about this reaction here. Question asked, calculate the mass of iron 3 oxide needed to react completely with 5.5 grams of aluminum. So our only concern are the reactants, okay? And we are given 5.5 grams of aluminum, 5.5 grams of aluminum. How many grams of iron 2 oxide is needed is the calculation, okay? Don't care about the products because they're going to be there, because our only concern is how much of the reactants we need to get this reaction to proceed. And this is typical what we normally do in the lab. We figure out how many grams of one material we need, one reactant, and determine how many grams of the other one we need. Okay. All right. So obviously we're in grams. So the very first thing we need to do is to convert the grams of aluminum to moles of aluminum. Okay, and we'll come back to that in a second. Then we're going to have two questions. The second question, in this case, let me clear this up a little bit. Let's calculate the mass of aluminum oxide. Aluminum oxide is a common material used as an abrasive. I think you might find some of your nailing polish things, you know, for your nails. That sandpaper, I remember put it that way, sandpaper, you'll find some aluminum oxide in there. Calculate the mass of aluminum oxide produced when 10.25 grams of aluminum reacted completely. And so those are who we need to be concerned about, just those two compounds. Okay? Yeah, there's a question. Oh, this one, no, there's something else, Skylar, I'm not 100%. There's not 100% on that one. I know thermite is used, but there's something missing on it. I have to look that up. But don't try this at home, just in case. All right, so that's what we're looking for, those two. So identify, we did both. We're gonna now, let me clear this up. We're going to do the first one. So we got 5.5 grams of aluminum. So the first thing we need to do is convert those grams to moles of aluminum. So what do we need? We need, in this case, we just simply need the atomic weight, right? Because it's the element. So the atomic weight of aluminum, which we find in the periodic table, is 26.98 grams per mole. Notice I set it up with moles in the numerator, grams in the denominator, okay? Why? Because I want grams to be removed, and I'm searching for moles because I got to get from apples to oranges, and the only way to do that is through moles. Next step is I got to use the stoichiometric relationship between the iron 2 oxide and the aluminum, okay? And so as we proceed with this, it may look a little bit foreign here, but check the units out. Do not grams of, let me change the color here, a little bit brighter. Do not grams of aluminum cancel, grams of aluminum here. Moles of aluminum cancel, guess what? Unit-wise, we are now in moles of iron 2 oxide, okay? We have converted from the apple to the oranges, okay? But only when we went through moles. Now that we have moles of iron 3 oxide, we need to get to grams because, again, we're in the world, we're not measuring out in moles, we are measuring out in grams. So we need, in this case, molar mass. So we look up the atomic weight of iron, atomic weight of oxygen, and that gives us the molar mass, okay, which is 71.85 grams per mole. Note the units, follow the units as I proceed, because like I stated, if you set that up properly and you follow the units, you're in the right track, okay? And now, at this point in time, it's a matter of you doing the math. 5.55 divided by 2698, multiplied by 3, divided by 2, multiplied by 71.85. Okay. And you should end up with 22.2 grams. Now, what you just calculated was the following. That if I start off with 5.5 grams of aluminum, I need 22.2 grams of iron 2 oxide for this reaction, okay? Now, if I wanted to calculate how much of the other products I made, I can do that, given any of these numbers. Okay, I can calculate how many grams of iron or how many grams of aluminum oxide I make with these numbers. Okay? In fact, that's the next problem, where we are starting with 10.2 grams of aluminum, okay? And I think, yeah, this one we're going for aluminum oxide. So the first step, as we did in number 1, is to convert the aluminum to moles, okay? Second step is we need the stoichiometric relationship between the aluminum oxide and aluminum. All along, I am keeping track of my units to make sure that I set that up properly. My grams cancel, aluminum, moles of aluminum cancel, and lo and behold, there I am. Unit-wise, I'm at moles at aluminum oxide. Next step, like we did in number 1, I got to convert that to grams. And so I need the molar mass. I have 2 aluminums, 3 oxygens, okay? And that adds up to 101.96 grams of aluminum oxide per mole of aluminum oxide, okay? Again, take the units out, and this is an example of show your work. In other words, you show everything you need properly, all of the conversion factors are there. You follow this technique, this dimensional analysis technique, and like I said, 99.9% of the time, I guarantee you're correct. You'll be set that up properly. I don't give you the full 100% because you have control of the calculator. I can't, you can inadvertently type in the wrong number. But a problem like this could be, for example, how does that work? Well, I could, normally what we do is we say, maybe this question is worth, let's say 5 points, right? All right. So, there's your answer right there. And that answer is like 1 point. And so what's left, the other 4 points are, spread out amongst how you set that up. So that means that if you just present the answer of 19.37 grams and it says show the work, then I can only give you 1 point, okay? And the converse of that is this, if you present your work with all the conversion factors and you inadvertently type in the wrong number and your answer is wrong, well, I'm only going to take off 1 point because you earned the 4 points because you showed the work, okay? All right, so any questions about that part? Rehash all this, balance chemical equation, okay? Stoichiometric relationship, take your grams, convert them to moles. From the moles, that's the first conversion factor. Your second conversion factor would be the ratio stoichiometric relationship between what you're looking for and what you're given. And then that gives you the moles of what you're looking for, what you're trying to find. Then the atomic mass, molar mass, or atomic weight of what you're looking for is put in there, and you end up with grams of what you're trying to find. Okay. So like I said, you have at least at the minimum 3 conversion factors. Okay. And all of them go through moles. That's the key part. You got to get to moles. Now, if we were doing a different kind of problem, we won't introduce that right now. All right, so here's the flow chart that incorporates the STP, standard temperature and pressure. Remember, 0 degrees of 1 atmosphere scenario. And that's in the bottom left, bottom right corner there, where you're dealing with gases. Now remember, for that to be true, you have to be at STP only. Okay. Hence, you can't get to the yellow blocks without being an STP. If you are an STP, I mean, you can go any multiple ways here. I mean, I can go from, and I can go from grams given all the way to volume fine. And I gave a double arrow there because you can, it goes both directions, okay? You can be given moles of a gas, grams of a gas, and you got to work backwards to figure out grams given or grams fine, you know? And again, you can go from the top right to the bottom left corner, double arrows. Or you can just go like we've been doing right here, right through here. This scenario, okay? Or you can go the bottom scenario. Either way, the point is you've got to go through moles, plain and simple. Like you got to get through moles to get from anything, to get to anything from anything. Yeah. Okay, so this flow chart here, use it when you do these calculations, because eventually, you know, the more examples you do, it'll be like it'll kick in. You'll say, oh, okay. But remember, I got to get from grams to moles, from moles to using the mole ratio to moles of what I'm looking for, and from moles of what I'm looking for, I need the molar mass to get me to grams, what I'm looking for. Okay. And that's what the given and the grant and the fine is all about. No. All right. Let's do this example here. This is right and balance the reaction of hydrochloric acid and solid cobalt. Okay. Well, let's work it out. And so we have solid cobalt, CO, plus HCl, hydrochloric acid, aqueous. And it's an acid. And if you remember, I said all metals reacting with hydrogen is more reactive here. Or cobalt, cobalt's more reactive. So we're going to make hydrogen gas plus the salt. And it's telling you here that cobalt will be in the +2 state. You have to know that because cobalt is a variable oxidation state, and it's not part of the 16 that we would know its oxidation state. So you have to be given that bit of information. Then the corresponding hydrochloric, the chlorides, going to be there. So those are negative, right? Because group 7 ions are picking up 1 electron. So we need 2 of them. So we're going to make cobalt chloride fused aqueous. Okay. We're going to balance this out. And if we put a 2 in front of HCl, do we not balance the chlorides and the hydrogens? Sure do. Okay. All right, so that looks reasonable. Let me clear this up and better picture. All right, there we go. Now, the question is, how many liters at STP will form if 5 grams of cobalt reacts? All right. So let's identify who we are dealing with. First of all, we are at STP. What does that tell you? 22.4 liters per mole. Okay. Second one, how many liters of gas at STP will form if 5 grams of cobalt reacts? So we got 5 grams. And they're asking how many liters of gas? Well, the only gas that you're going to make here is obviously hydrogen gas. Okay. And so that's who we're dealing with right here, between cobalt and hydrogen gas. All right. Well, cobalt is in grams. So we need to convert that to moles. So we need the atomic mass of cobalt. All right, so we're given 5.5 grams of cobalt. Find its atomic mass, its atomic weight, which is 58.93 grams, okay? That gives us, let me clear this up a little bit. That gives us moles of cobalt, okay? While we're at moles of cobalt, we use a stoichiometric relationship from the balanced chemical equation to give us moles of hydrogen, okay? So you see where we're at here? Check the units, grams of cobalt cancel, moles of cobalt cancel, leaving us at this point with moles of hydrogen gas, which could be good, okay, if that's not if we were looking for moles, but we're looking for liters. And so given that we are at STP, well, then we can add the 22.4 liters per mole. Okay. That means that now we are in liters of gas. And so to rehash that using we went from the far left of the flow chart, grams given, all the way to the bottom right of the flow chart. Okay, you see that? So we use molar mass of cobalt, the mole ratio between the reaction that gives us moles of hydrogen gas, and then being that we are at STP, we have the volume of gas. And we can only do that if we were in fact at STP. If we were not at STP, you cannot calculate that final volume. Okay, you can with a different equation we will learn about in chapter 16, but at this point, nope, unless you're at STP. Okay. All right. Clear the mess up a little bit. If 2.374 liters of hydrogen gas is formed, how many grams of hydrochloric acid reacted at STP? And so now let's identify where we at. If you made 2.374 liters hydrogen gas, question is, well, how many grams of hydrochloric acid were given? Okay. And so where we did on the flow chart, we went from the top left to the bottom right. It sure looks like we're reversing that, right? We're starting backwards in the flow chart. Remember in the flow chart, we went from the first question, we went from grams given all the way to volume find. All right. Now you're going to go from volume given to grams given. So you're going from the bottom left, work your way backwards to figure out how many grams. Okay. Okay. See, volume given back to grams of hydrochloric acid. So it's the bottom left corner of that flow chart to the top left corner. Or it could be a top right corner. Either way, you're looking for grams at the end. So we write down what we're given. 2.374 liters of hydrogen gas. Okay. We're at STP, so we convert that hydrogen gas into moles of hydrogen. The stoichiometric relationship between hydrochloric acid, HCl, and hydrogen gas is a 2-to-1. That comes from the balanced chemical equation. Okay. So keeping track of the units, you can see at this point, mathematically, we would end up with moles of HCl. The question asks us to calculate the grams, so we need one more conversion, and we need the molar mass of HCl, which is 1 chloride, 1 hydrogen, 36.46 grams per mole. Check your units. Unit-wise, we end up with grams of HCl. So everything's been set up properly. Now it's a matter of plug in the numbers in the calculator. You should end up with 7.27 grams of HCl. Now you might ask the question here, why do I have 3 sig figs at the answer when I started off with 4 sig figs? Okay. Anybody answer that? Why do we end up with 3 sig figs when I started with 4 sig figs and 2.374? Atomic weights? No. Atomic weights aren't utilized in determining your sig figs because, again, there are average of whole numbers, which have an infinite number of sig figs. Okay, so that is correct. The 22.4 liters is a measurement. It's not an exact number in this conversion factor. So that could play a factor in the final sig figs, and it does here. Okay. All right, and not so much in the first part, because the first part we had 5.00, which had 3 sig figs, and then the 22.4, which has 3, so our answer has 3 sig figs. But don't forget about the 22.4. It has 3 sig figs. That is correct, Skyler. Now, let me clear this out. Now, hydrogen gas plus oxygen produce chlorine gas and water vapor. So we got to be a little careful here because chlorine gas is a poison. Okay, so we're given the reaction in words, and we need to convert that into an equation. Okay, so HCl gas, which is given HCl gas plus oxygen, produces, which is the arrow, the reaction arrow, chlorine gas, which is diatomic. Okay, a lot of people forgot about these diatomic gases in the exam. Remember, have no fear of ice cold beverage. There's only 7 elements that are diatomic. Chlorine is one of them, hydrogen, oxygen, nitrogen, etc. Okay, and it produces water as a gas, water vapor. Now notice something interesting. The reactants and the products are gases. Note that, okay? All right, so after we do that, we wrote down an equation, we balanced it, and we end up with 4 HCl. By the way, HCl, when it's aqueous, being in water, is hydrochloric acid. When it's a gas, there's no water involved, it's called hydrogen chloride. Now, I've been given credit in the nomenclature exam, whether you did hydrogen chloride or hydrochloric acid, because we didn't really talk about it that much as far as nomenclature. Just want you to be aware of that. Aqueous system, so that would be like HBr would be hydrobromic acid versus hydrogen bromide. Is the gas. So 4 HCl's plus 1 oxygen gives us 2 chlorines and 2 waters. Okay. So I'll balance, everything looks correct. All right, so the question here is between how many liters of chlorine can be formed if we start off with 3 liters of oxygen. 3 liters of oxygen, how many liters of chlorine can we create? And We are at STP, which again, we can use at 24.4 liters per mole scenario if we need it. So break down what we're given, 22.00 liters of oxygen, okay? Get us 2 moles of oxygen using the 1 mole per 22.4 liter per mole, okay? Then we use a stoichiometric relationship between the chlorine and the oxygen, which is a 2-to-1, okay? And that gives us moles of chlorine. So for moles of chlorine, we got to go back to volume, right? Because that's what the question is. How many liters of chlorine do we create? So we go back to the 22.4 liters, and that tells us that we're going to make 6.00 liters of chlorine gas. Now, if we look at the way we set this up, can you guys see a shorthand way, which is only true if the reactants and products are gases and that you are at STP? Can you see that the 22.4 and both sides cancel each other out? And so under these conditions, and only under these conditions, see, these cancel out right here, right? So the only thing we need is a stoichiometric relationship between the two reactants when we are, both products are gases. Okay, it won't be true. One of them is not. One is aqueous or a solid. So you can see the 22.4 liters cancel out. So, but if you don't see it, don't worry about it. Just continue with the 22.4 liters, and you'll see. You know, as you do more of these, you see, oh, okay, that cancels out. So I can shorten it a little bit, shorten the calculation. All right, so. All right, try these at home, and we can bring them back on Tuesday. The question is: carbon reacts with oxygen gas to form carbon monoxide. Okay, how many liters of carbon monoxide at STP can be made from first question would be if you start off with 15 grams of carbon dioxide. How many liters of carbon monoxide can you make? Or if you start off with 20 liters of oxygen gas, how many liters of carbon monoxide at STP can be made? Okay, you should end up with that answer there. Anyway, come back on Thursday, try it out and see if you can work it through. If not, we'll talk about it on Thursday. These calculations, what we did is basically what we've done is take the elements, create them into compounds, be it ionic or be it covalent, okay? From the compounds, we had reactions, then we balanced the reactions. From these balanced reactions, that we have stoichiometric ratios that we utilize, that we can do calculations of reactants or products based on these ratios. And we can calculate the answer in terms of either moles, grams, or liters of gas if we are at STP, okay? And this flow chart is very important. This will aid you and guide you through these calculations, because sometimes it can be very overwhelming that you see these problems. And these kind of problems you really got to work through, because I remember taking exams to get into schools, like the SAT. I think they did the ACT at the time. It's been a while, but it was a formalized question. I remember questions like, you're sitting in line at some place, and some ladies and 3 people in front of you, she's wearing the blue hat. People behind you are wearing the yellow hat. What kind of hat, what color hat you're wearing, and what time is it in China? I'm like, what? It's crazy questions that you see no connection. And in order, my suggestion is this: break it down to pieces. Break down what you're given, what you know. Write those pieces down. Use this flow chart, and even though it may seem like you're totally disconnected, all these equations are really connected. And the key thing is keep in mind moles. moles. How do I get from where I'm at to moles, and then from that mole ratio, and that'll get you to where you need to go to, okay? And keeping track of your units all the way along the road. So with that in mind, congratulations, you are done with chapter 13. All right. Tell you what, let's take a 10-minute break. I got 2:07. Let's go, I call it 2:20, okay? 2:20. And we'll be back. Well, welcome back. Skylar, you had a question earlier about that aluminum iron oxide. I did look it up. It's normally iron 3 oxide that is utilized for aluminum. If you want to, you guys want to look up a very impressive reaction, look up thermite. You'll see it. It's iron 3 oxide and powder aluminum. It's not spontaneous reaction. It requires high temperature to ignite it. It's quite impressive. It gets so hot that the iron, which is a single replacement reaction, the iron that is created is soft. It melted. It's liquefied. It's so hot. Yeah, but quite impressive. Yes, exactly. Just the power of the amount of energy that's in chemicals is it's mind-boggling when you think about it. If you could just think about, not far from us, there is a big nuclear reaction that's occurring that powers you with electricity, and that's the power of the atom. Okay. So anyway, this brings us to chapter 14. And this particular chapter deals with intermolecular forces. Now, what we're talking about are interactions with other molecules in themselves, okay? Compared in contrast to intra, INTRA, is those forces within the molecule, specifically the type of bond they have, be it covalent, be it ionic. Now, the intermolecular forces, those are interactions that occur with molecules with each other that have a big factor on the properties of those compounds. Now, you need to go back and refresh your memory with respect to polarity. We did mention way back when that polarity shows up time and time again, and this is another example that these forces, there's only 4 of them, 4 forces. And the type of molecule you have determines what type of force that you're going to be utilizing. And so go back and refresh your memory about a molecule that's either polar or nonpolar, and obviously ionic compounds, okay? Now, these forces really deal with the electrons surrounding those molecules, and that's these crazy electrons. They have a big factor. And that's why certain things boil at certain temperatures. Water, for example, boils at 100 degrees. Ethanol, good old-fashioned drinking alcohol. Very similar to water with respect to polarity. Similar, I didn't say the same now. But its boiling point somewhere in about 78 degrees Celsius. A little bit different. And again, it deals with the intermolecular forces that are involved with respect to the molecules. Okay, this diagram here kind of distinguishes between the two. The intermolecular forces, here's 2 molecules, 2 diatomic molecules. The intermolecular forces are denoted by the dashed line and how molecules interact with each other, okay, versus the intra forces, and those are the bonds within the compound, okay? Now, intermolecular forces hold molecules together. Now, they're not bonds, they're forces. Some of them are stronger and some are weak relative to the forces within them. Now, with respect to bonds, they're very weak. respect to an actual bond strength, it's extremely weak. But with respect to forces within the molecules, we have one force that's very strong, and then one force that's fairly weak. Okay, and that affects certain physical properties that we're going to talk about. We're going to be able to compare and contrast two molecules, and in that we can't really give absolute values with respect to the physical properties, but we can give relative effects. We could say such things that molecule A would expect to have a higher boiling point than molecule B, okay? Simply because of the type of forces that they have. Now, bonds versus IMF, I'm pretty sure we're pretty consistent or understand now that we're talking about bonds, we're talking about polar bonds, be it non-polar bonds or polar bonds. These are covalent bonds, okay? Then ionic bonds between metal and non-metal partners. Refresh your memory on those, okay? Now, with respect to intermolecular IMF, that's the interaction. Hydrochloric acid, those interactions can be very, very strong, okay? And have a drastic effect on the physical properties. Now, there's 4 types of intermolecular forces, okay? The first type is called London dispersion forces, okay? Point number 1 about London dispersion forces. All polar, excuse me, let me restate that. All non-polar molecules have, the only force they have is London dispersion forces. Okay, let me repeat that. All non-polar molecules have London dispersion forces. So that means go back and review how to determine whether a molecule is polar or non-polar. Okay, because that's going to determine what type of force they're going to be affected by. We have what are called dipole-dipole forces. That's where 2 dipoles come together and they interact with each other, okay? And so DDF, dipole-dipole forces, generally are covalent compounds that have a permanent dipole, okay? That is a bond between 2 dissimilar atoms, and one atom has a higher electronegativity than the other, resulting in a dipole, permanent dipole. Therefore, their force is the dipole-dipole force. Okay. London dispersion forces, think about this. All of the diatomic molecules have London dispersion forces. All hydrocarbons, because they have nothing but carbon-hydrogen bonds, have London dispersion forces. Those molecules that had polar bonds but canceled out have London dispersion forces, like carbon dioxide. Remember carbon dioxide, we talked about that. They have 2 polar bonds, but because the way they cancel each other out, it's a nonpolar molecule, hence the only force they have is London dispersion. Tetrahedral compounds, they have 4 polar bonds. The geometry of those compounds cancel those 4 polar bonds out, therefore they have London dispersion forces. That means that all the other guys have polar, anything that's polar will have dipole-dipole forces, okay, or interactions. Now there's a special kind of dipole-dipole force, and we call that hydrogen bridging. You might see the name hydrogen bonding, but it's not a true bond. It's an interaction. It's really a force between them. Now, these are only special, though they do have a dipole-dipole. They're special in that only applies for those hydrogens, hence the term hydrogen, that are bonded to nitrogen, oxygen, or fluorine. Okay? And so if I have nitrogen and I have bonded to it a hydrogen, like say ammonia, or I have oxygen bonded to hydrogen like water, or I have fluoride that's bonded to hydrogen like hydrofluoric acid, okay? only in those scenarios there are dipole-dipole force. However, because of those special conditions, they have their own special additional force, which is a little bit stronger than the dipole-dipole force. And those are called hydrogen bridging force. You may find that old literature also call this hydrogen bonding force. But I emphasize the fact that it's not a bonding, because what's happening here is they're interacting with another molecule. Okay, we can draw it like that, the dotted line. Okay, and it's a much stronger force than, say, London dipole-dipole. Now, with respect to strength, these three, hydrogen is the strongest interaction. London dispersion forces is the weakest, and dipole-dipole is somewhere in the middle. So London dispersion force is weakest, dipole-dipole in the middle, and hydrogen bonding a little bit stronger. Now, the last force is called Ion-Dipole Force. The term ion should tell you something right away. That when we're dealing with ions, obviously we're dealing with ionic compounds. Numbers 1 through 3, we're dealing with covalent compounds. Covalent. Okay. Here, number 4, we're dealing with ionic. Oh, ionic. Oh, somebody coming in. One second here. Okay. Ionic compounds, hence the term ionic, which is normally dispersed in if it's ionic, then it is dispersed in a aqueous system. So the dipole force generally is coming from an aqueous system like water. Okay. And so if you're asked to determine whether the system is what kind of force, the fact that you see an ionic compound in water is number 4, simply put, nothing else. They're not, ionic compounds had nothing to do with covalent bonds. And number 1 to 3, nothing but covalent bonds, okay? All right, so let me rehash a little bit. London dispersion forces, the weakest. All non-polar molecules have nothing but London dispersion forces. Polar molecules have dipole-dipole, okay? And polar molecules, specifically the special cases only, they have hydrogen bonded to nitrogen or oxygen or fluoride. They have an additional force, which is not overwhelms, but is stronger than the dipole-dipole force. And that's called hydrogen bridging, also known, the old naming was hydrogen bonding. And then ion-dipole forces deal with an ionic compound, normally within an aqueous system. Okay. Now, London forces, because the molecules are nonpolar. Okay, these forces are temporary. The best analogy I can think of is if you ever have taken a balloon and you rub it on your head and then you put it on your chest. Does not the balloon stick for a period of time? Yeah. Any idea what might be happening there with the balloon other than Harry Potter magic? No, you get the balloon, rub it on your head, and then place it on your chest, and it sticks to your chest. What do you think might be happening there? And what we got here? Electrons attracting. That is correct. Hold on one second, drop something. What's happening is this. Obviously, the balloon is loaded with electrons. Now, after you rub your hair, we got electrons all around us. You ever wake up with a bad hair day, your hair is like, poof, right? Or you put on the clothing and it kind of sticks to you, or you may be pushing a cart in the grocery store, and sometimes the wheels kind of rub and build up electric charge, and then you touch something, you get zapped. Or better yet, walk on carpet and then touch something, brand new carpet. Okay. Well, what's happening is you're taking those electrons on your head and you're transferring to the balloon. Okay. Now remember, the electrons have a negative charge. And now on the surface of your chest, you have electrons too. They're all around us. Okay. Now what's happening is as you push those electrons toward your chest, the electron negative charge on the balloon are repelling the electrons in your body and pushing them kind of into your body, resulting in an area that's a lot more positive, just like a dipole. And so you have on the surface of your chest an area that's more positive in charge. Here comes the negative charge of the balloon, and guess what? They stick. Now, obviously, they're not very strong. That interaction, it'll hang there for a while. Eventually, everything, Mother Nature being Mother Nature, you go back to equilibrium, and then the balloon falls off. Okay, and so that's what these forces are. They're temporary forces between nonpolar molecules, and it's simply because they kind of, whereas polar molecules have a permanent dipole, nonpolar molecules have what we call induced a temporary dipole. They created a partial negative and a partial positive side to get that attraction. Now, the thing about this is that the bigger the nonpolar molecule is, when we compare nonpolar molecules within each other, all of them have London dispersion forces, but some of them, because of the size, have stronger London dispersion forces because there's more of it. Okay, more of it. It's very similar, analogous to most vegetable oils are hydrocarbons made up of nothing but carbon and hydrogen. There's some other parts to it, but the majority of it is hydrocarbons. Okay, and most vegetable oils are liquid, as compared to some things like lard, which also are made, like butter, for example, are made up of hydrocarbons, and they have more solid character. Okay, because there's more of that nonpolar interaction. Those molecules attract to each other a little bit better, a little bit greater, so they become more solid in nature. Okay, as compared to, say, a liquid vegetable, there's less interaction, London force interaction, and hence they have more liquid nature into them. And it's all the result of the interaction between these molecules with each other. We know that, for example, that honey is pretty thick, but what do we do to make it flow a little bit greater? We heat it up. When we heat it up, what we're doing is we're breaking up the interaction of these molecules with each other, making it interact less and make it more liquefied. Okay, so bigger molecules, more electrons, more London force. Okay, and this basically kind of demonstrates what's happening here. You kind of induce a temporary partial positive and a partial negative side due to these electrons moving around. Okay. Now, dipole-dipole forces, permanent dipole, whereas London forces, nonpolar molecules have a temporary induced dipole. These compounds have a permanent dipole because of the difference in electronegativity of the two that are bonded to each other. For example, hydrochloric acid, HCl. The chloride has a higher electronegativity than hydrogen, therefore it will, just by the nature of the beast, will pull electrons onto itself, resulting in a permanent dipole, okay, and a permanent and partial negative side to the HCl molecule. And then the partial negative side then interacts with the partial positive side of another molecule, okay? And here we show it here two-dimensionally, but keep in mind that we live in a three-dimensional world, so then it's not just happening right there in two-dimensional, but above, behind it, and so forth, and behind the screen and so forth in a three-dimensional world. Okay, dipole-dipole forces stronger than London forces, but Obviously they gotta be a polar molecule with a permanent dipole. Now, hydrogen bridging forces. It's very strong dipole force between molecules that contain hydrogen, fluoride, hydrogen, oxygen, and hydrogen, nitrogen bonds only. NOF to help you remember it. I don't know, not on file, something like that. Nitrogen, oxygen, and fluoride, and only for the hydrogen. And very strong interaction. Water is very polar, very strong hydrogen bridging forces. Okay, and this diagram here shows you again in a three-dimensional model, if you will, of all these forces of these molecules interacting with each other. These interactions affect such things as boiling point, vapor pressure, surface tension, and viscosity. Those are the four physical properties that we're going to be using to do a compare and contrast. All right, so very much stronger than a simple dipole-dipole force, okay? But still, all these forces are much weaker than the actual interaction between an ionic bond and a bond strength of a covalent bond. The ion-dipole force, well, that's simply an ion. In this case, is showing an example of sodium ion that is solvated with water molecules around it. Sodium ion has a very strong, a full positive charge. And so the water molecules being polar, obviously, has a very strong partial negative side, and they surround the partial positive or the full positive of the ion. And the same would be true for the counter anion. The positive side of the water would be solvating that. Okay, so it's very strong interaction, extremely strong interaction within there. So summarize the bond versus forces. We know bonds, we got ionic bonds, holds metal, non-metal ions together. Polar covalent bonds, okay, there's a sharing of bonds, but in this case, an unequal sharing because one atom has higher electronegativity than the other. And non-polar covalent bonds where we have equal sharing of those electrons, okay? With respect to forces, and those are the bonds we dealt with, three types of bonds. Okay, the forces, we've got London forces that apply only to nonpolar molecules, and dipole forces, which apply to polar molecules. And then we have the hydrogen bridging force that applies, which is a dipole force. However, it applies, has its own little special name, and applies only to nitrogen, oxygen, and fluoride that have hydrogen bonded onto them, okay? And then finally, the ion-dipole force, which normally is an aqueous system in some type of ionic compound. So what do? We got a table here where we have the molecule, and then they're asking you here, is it polar, non-polar? And then from that information, determine its strongest intermolecular force. Well, here, this is where the Lewis dot structures come into play. If you forget, and whether, if you want to know whether a molecule is polar, go back and refresh your memory on Lewis dot structures, for example. That would help because we would think that carbon oxygen would be polar because of the polar carbon oxygen bond. However, once we do the Lewis dot structure, if you recall, we did that. We saw that the carbon hydrogen oxygen bonds were opposite of each other. It was AB2 general formula, and that they canceled each other out. Therefore, it became a non-polar molecule, though they had polar bonds, okay? So it's non-polar. Once we identify it as what polarity the molecule is, automatically, since non-polar, the only force they got is the London force, that's carbon dioxide. Doing the Lewis dot structure of trifluoride, phosphorus trifluoride, we find it to be very similar to ammonia, NH3, where we got a lone pair on the central atom, which right there just tells me automatically, I got a polar species, okay? And sure enough, we got a polar species. And the only thing we got to deal with here is the dipole-dipole force, okay? not the London, not the hydrogen bridging, because first of all, there's no hydrogen involved here, like the next one, which is HF, hydrogen fluoride or hydrofluoric acid, if it's aqueous, is a polar bond. So we know that part. Now the question is it dipole-dipole? Well, our first thing we would think is, yes, it's a dipole bond. However, it is one of those three atoms, nitrogen, oxygen, and fluoride, that have a nitrogen bonded to it. So it has hydrogen bridging force. Okay, CH3. Recognize that we have nothing but carbon and hydrogen. Automatically, don't have to go any further. We know that is a nonpolar species. Okay. Which again tells us automatically it's a London force. It's the only force they have. And then Ki, and then we got its state as an aqueous, right? So we have automatically ionic compound and an aqueous solution. Has nothing to do with the three forces we've been dealing with. It's simply its own little force, if you will. It's an ionic compound in polar water, so it's simply an ion-dipole force. Okay. Don't want to say much about Coulomb's law. There really not much to say here. It's basically saying, in a nutshell, we're not going to expect you to memorize this or anything like this, because what this is just saying is this, and this is something you already know. You probably observed it. If you simply get two magnets, okay, and you bring them, let's say you got the north and the north of the two magnets, and you bring them together, north and north, right? As you bring them closer together, you can feel that force of repulsion. Or you can bring the north and south together and you can feel that force of attraction, but don't let them touch. You can really see it dramatically if you put the opposite or the same north and north or south and south. And the closer you get, the stronger the force. That's simply what's telling you here. And it happens to, the force tends to go increase as by a factor of 1/r², which is the radius square between the two that are coming together. It just shows you it's very stronger, and as the closer you get by a large factor. Okay, that's all we got to remember. K is a constant. Q, both Q's are just the charges, so we can generally put those as a constant and only look at the r square, which is the inverse. Now, the other thing here to remember is things that are inversely and directly related. When something is directly proportional to a variable, for example, if a variable A goes up by some magnitude, then variable B also goes up by a similar amount of magnitude, okay? Basically, one factor goes up, the next goes up. A good analogy would be, hey, you study hard, I get good grades, right? Grades go up. Okay. What's inversely proportional means that when one variable goes up, the next one goes down. That's not what you want to do. If you study hard, you don't want your grades to go down. You might think that's what happens, but no, that's inversely proportional. One goes up, one goes down. Okay, that's what they're telling you there. All right, let's look at the table here. Now, to answer these questions carefully, read the question carefully. Are they talking about one molecule? As I put two fingers up, one molecule, or are they talking about two molecules interacting with each other? Okay, so the first one says, what holds the atoms together in one ammonia molecule? Well, obviously, we're talking about the type of bond within the molecule. And what we know about that it is a polar covalent bond for the NH, okay? What is holding the sodium ions in water? Okay, now we got ions. Water is a dipole polar solution. So that's the only thing there would be the Ion-Dipole Force, okay? What is holding three HCl molecules together? So we're talking about three hydrochloric molecules, HCl molecules, in what's holding them together? So that would be intermolecular forces. We look at the molecule HCl. Okay. Obviously, it's not ion-dipole. There are no ions involved here. We know that HCl is polar, so therefore we can eliminate the London force. And the only thing left is either dipole, or hydrogen bridging. We can eliminate hydrogen bridging, even though we've got hydrogen here, because hydrogen bridging is only for those hydrogens bonded to nitrogen, oxygen, and fluoride, of chloride not being one of them. So the only thing is dipole-dipole forces. Okay. What is holding the ions together in salt, sodium chloride? No water involved here. Okay, no aqueous system. You're just talking about salt. So I have to assume they're talking about solid material. And so therefore, that's simply an ionic bond, okay, with the sodium and the chloride. Okay. What is holding 4 H2O molecules together? So here we're talking about intermolecular forces again. And so water, H2O, is not polar, so that eliminates London forces. We have no ions here, that eliminates ion-dipole. So we're back to dipole-dipole, hydrogen bridge. Well, water is very unique, okay? It has hydrogen bonded to oxygen, so the only thing here is hydrogen bridging force. Okay? What is holding nitrogen gas molecules to each other? And so we're talking about molecules and other molecules, right? So it's intermolecular forces. So what do we know about nitrogen? Nitrogen is nonpolar, therefore London forces. What is holding the oxygens together in an oxygen gas molecule? Again, we're talking about intramolecular forces within the molecule. So we're dealing with non-polar covalent bonds. And then holding 2 ammonia molecules together, now we're back to inter. Okay. What do we know about ammonia? It's polar. Therefore, yeah, no London forces, no ion-dipole forces involved here. So it's either dipole-dipole or London bridges. Ammonia is NH3. So it is hydrogen bonded to nitrogen, which is the hydrogen bridging force. So again, by reading the question, and then if you need a process of elimination, what it's not, you're going to be eventually left with what it is, okay? And you might end up with 2 choices, and then remember the difference between dipole, and London bridges. This flow chart kind of helps you summarize the IMF interactions, okay? If it's covalent, obviously it's going to be nonpolar, then you go directly to London forces, no questions asked. If it's polar, well, if we're dealing with ion in there, then it's going to be ion-dipole interaction, okay? If it is a permanent dipole and it's not nitrogen, oxygen, and fluoride bonded to hydrogen, then the only choice you have is dipole-dipole. There's only 3 choices with respect to hydrogen bridging, and that is any molecule that has nitrogen and hydrogen bonded to either nitrogen, oxygen, and fluoride. Okay. So what effect does it have on these properties? One is vapor pressure, boiling point, surface tension, and viscosity. Okay. They're all related. Now, when you think about this, think about how the molecules these are intramolecular forces. So if I'm holding on, if the interactions between I represent a molecule of some sort, and there's another one next to me here. If our interactions are strong, then it's going to have an effect on these physical properties. For example, what do we mean by vapor pressure? Well, we're all familiar with this, okay? If you take a soda pop bottle, and I put a cap on it like I got right here. Oh, you see right here, a good old Coke. All right, obviously we got carbon dioxide in here, okay? Now, in the space, the empty space, we have carbon dioxide in the gas space up in there. Okay. That is gas, carbon dioxide. If we had a meter of some sort, a pressure gauge that we can put on the side of this container up here in the gas space, it would get a measurement, just no different than getting the air pressure of your tire. Okay. We know if I take this bottle and it still had the pressure gauge and I shake this soda pop up, carbon dioxide starts to bubble up, that pressure will go up and my pressure gauge will measure. But that is vapor pressure. Okay. That is the vapor pressure of the liquid. Now, down here in the liquid, think of this real good now, is if the molecules in the liquid hold on to each other tightly, there's going to be less gas molecules in the empty space. Okay, remember that. The less the less force that holds these molecules together, the greater the vapor pressure, and the converse is true. Okay, the greater the force holding the molecules together, the lower the vapor pressure, because there's less molecules going into being allowed to go into the air, okay, into empty space. And the same is true for boiling point. If a molecule is holding on to its molecules tightly, it's going to take a lot of energy to break up that interaction to shove those liquid molecules into the gas phase. And that is, for example, why water boils when I compare the boiling point of, say, water with ethanol. Well, water holds on to those molecules at a greater force than, say, ethanol, which boils at 78 versus 100. And so when 78 degrees comes in, that's enough energy to drive off the ethanol alcohol. However, I need to go all the way up to 100 degrees to get enough energy into the system to start the water to boil. Okay. Surface tension, that's how they act. Whether something beads up, you've seen liquids that you put on the surface, they may bead up or they may flatten out, depends on the surface tension. And so if molecules are held on to each other tightly, they're going to tend to bead up more on the surface than other molecules that don't hold on to the other compounds or other chemicals that don't hold on to the molecules as tight, and they may flatten out. So we won't get a bead of liquid on the surface. And viscosity, that's just a measure of a resistance to flow. We know that a cup of honey and a cup of water, honey is a lot more viscous than water. So if you had a little competition, see who wins the race, obviously water will win the race when we're trying to empty a cup of honey in a cup of water. And that's because the molecules of the honey are holding on to each other at a greater force than the water. Now, how do we make the honey flow a little bit greater? Faster? We heat it up, right? Heating up the honey breaks up those interactions a little bit more, and it reduces the viscosity of the honey. All right, so we're going to be looking at these now. Keep in mind, we're going to compare and contrast molecules with these properties here, but we're not going to be able to give absolute values. All we're going to say that this molecule would boil at a higher pressure temperature than another molecule. Okay, that's all we can do, just relative higher, no. So vapor pressure, as I mentioned, that is in a closed container, the amount of liquid that has gone into the gas phase. Okay. Obviously, we know that if we take the cap off, it will eventually evaporate, right? Because the molecules are bouncing around with each other. But if we cap it, we're going to eventually build up a pressure. Okay, and that pressure is that liquid molecules that gone into the gas phase. And the more liquid we have, the more material going into the gas phase, the higher the pressure. Okay, The weaker the molecules hold on to each other, the higher the vapor pressure. And the opposite is true, converse. So vapor pressure is exerted by gas molecules above a liquid in a closed container. So the stronger the IMF, the lower the vapor pressure, okay? Because it takes more energy to break the intermolecular forces from the liquid phase to let them go into the gas phase, okay? And this diagram here, again, which one has a weaker IMF? Well, simply it would be A, right? Why? Because there's more molecules in the gas phase. More molecules going into the gas phase. And I see sometimes people have a challenge with this because, you see, notice we have more molecules in the gas phase compared to B. That means that these interactions in here must be weaker compared to B, where the interactions must be a little bit more stronger. And they hold on at this, given the same temperature for A and B, there'll be less molecules going into the vapor phase. For example, I'm sure all of you at one point in time have opened up a container of fingernail polish remover. You open up the container, that stuff is volatile. You really smell it pretty strong, right? And that would be indicative of somebody like something like A, because the interactions of the acetone or the compound of the acetone, that's what it is, fingernail polish remover, majority of it is called acetone. There's less interaction, so more of it is going into the gas phase, okay? All right. And the higher vapor pressure, well, obviously A would be. Why? Because pressure is a measure of how many molecules or how much matter you have in the container. You have a low tire pressure, right? What do? You go to the Quick Trip, Circle K, put more air into it. Aren't you? You're putting more matter, more air into your tire, hence the pressure goes up. Okay, and so A would have a higher vapor pressure, okay, but a weaker intermolecular force. Okay, boiling point. And this is also true for melting point. Sometimes we don't talk about this. Melting point, the only difference is melting point is that temperature that a solid becomes a liquid. And boiling point is that temperature that a liquid becomes a gas. Okay, so stronger IMF, we would expect a higher boiling point for the same reasoning again as we did previously, because the higher IMF means that the molecules are being held on closer and tighter to each other, and therefore would require more energy to break up that interaction to drive it into the gas phase, okay? And the same is true for the melting point. Okay. Yeah, okay, well, let me let me qualify that. When we talk about boiling point, we're going to talk about 1 atmosphere here, because obviously the boiling point changes depending on the atmosphere that we're at. So obviously the boiling point here would be a lot different than the boiling point in, say, Denver, Colorado, okay, because of the vapor pressure. So yeah, you got to talk about the boiling point at 1 atmosphere. We got to compare apples to apples. Yeah. Yes, and that would lower your boiling point, because the boiling point by definition is the temperature at which the liquid is converted to gas at whatever atmospheric pressure they're at. So you have a lower atmospheric pressure, your boiling point would be lower. Now, surface tension, basically, that's again stronger IMF. We would have a high surface tension. Okay, and that's really, if we look at surface tension, think about it, how a liquid beads up when we place it in the surface. Disregarding, you know, I don't want to introduce surface energy, what has to do with the surface. It's a whole new ball game here. But think of it in terms of the liquid beating up to an, say, let's for right now, just a neutral surface, okay? So that liquid will beat up an X amount versus a liquid that would just flatten out. It's analogous to, let's say you got your car just been waxed and nice and clean, you throw water in, it beads up. But surface tension, surface energy, big science. I was involved with this quite a bit in spraying of special chemicals onto material, and it's pretty intense field. But we're just going to think of it in terms of how much it beads up, where you can see here that A beads up much more than B, okay? And A would have the higher IMF, again, for the same reason, because they're holding on to their molecules much stronger than, say, B, okay? And therefore, B spreads out, whereas A does not as much. And viscosity is a measure of viscosity is a measure of the resistance of flow. So we know that oil generally depends on the weight of the oil, but a viscous oil flows slowly because of its high viscosity, okay? And water, or AKA vodka, flows rapidly, again, because of its low viscosity. Okay? Oh, Skylar, I was reading your question. How does the elevation cause a lower boiling point? Again, it's a measure of the atmospheric pressure and where they're at. And what the atmospheric pressure is, that's the boiling point. Okay, so less than 1 atmosphere at a higher elevation, to reach that level would require a lower amount of energy. Stronger IMF would give us a higher, due to a higher, lower, sorry, let me restate that. Having higher IMF causes a higher viscosity. So again, comparing honey with water, honey would, their molecules have a higher IMF interaction than water does, and therefore more viscous. Okay. So let's compare and contrast. So it's a typical compare and contrast. We're going to look at ammonia and we're going to look at fluorine. Well, before we can do anything, we need to write the formulas. Now, refresh our memories. Formulas for ammonia was NH3, had lone pair sitting there. If you recall, we learned right away that this guy is polar, okay? Fluorine is diatomic, okay? Being diatomic tells us what? We are dealing with a non-polar species. And so we need the formula. In the formula, we need to determine whether something is polar or non-polar before we can even start to do a compare and contrast. All right, so we got the formula there. And then we know that nitrogen, or the forces, assign the forces. Hydrogen bonded to nitrogen. Obviously, it's a covalent bond. It's not London forces because it's polar. So, and plus it has nitrogen bonded to hydrogen. So the only thing is hydrogen bridging force. And London force for the diatomic fluorine molecule. Once we assign the IMF, now we look at it and say which one is stronger. Obviously, hydrogen bridging forces is stronger than London forces. So fluorine would have the weaker force, okay? The weaker force. And think about it in terms of the molecules. Nitrogen and the ammonia molecules are held onto each other stronger than the fluorine. Therefore, that's going to have effect on the properties, physical properties. So we just went through this scenario. Ammonia would have the stronger IMF because it has the hydrogen bridging force, okay? Which would have the lower boiling point. Well, the one with the lower boiling point would be fluorine because it has the weaker IMF interaction, okay? Having the weaker IMF interaction means that it would take less energy to break the molecules apart and allow them to go into the gas phase. All right, which is polar. Obviously, we talked about that. Ammonia is polar and fluorine is nonpolar. Which has a higher vapor pressure. Okay, now think about this carefully now. Now, the one with the higher vapor pressure would have the weaker IMF because then more molecules will go into the gas phase. In this case, fluorine will have a higher vapor pressure than ammonia because it has the weaker IMF. And if there were liquids, which would be at least viscous, then again, fluorine would not be as viscous as ammonia, simply again, because of the weaker IMF interaction for fluorine. And then more surface tension, that would be ammonia, because ammonia has the stronger hydrogen bridging force. All right. Now, the questions were asked in this manner, but they could easily be reversed. Question number one could say which has the weaker IMF, or question number two, which has the higher boiling point. You see how those questions can be changed around a bit. Okay. All right. This kind of helps you out here because summarizes. As the IMF increases, what do you think happens to the viscosity? Does it get higher or less? What do you guys think? It increases higher. There you go. And guess what? The same would be true for the boiling point. Remember that as the IMF interaction increases, the stronger IMF interaction, and we're talking about the three, the hydrogen bridging, dipole-dipole, and London dispersion forces. Okay. We're talking about those three. And so as the IMF gets stronger, they hold on to the molecules much stronger, and it takes more energy to break them apart. And the surface tension increases. The vapor pressure drops because there's less molecules in the vapor phase because the molecules in the liquid are held on to each other much greater. Okay, so the less chance of them to go up into the vapor phase. Doesn't mean zero chance, it's just less amount of them are go in there. Water, we kind of throw this in a special case with water. We talked about this. We did the Lewis dot structure. It has two bonding electron pairs, two non-bonding or lone pairs on it. It has the bent geometry. The bond angle is much less than 109.5. Water's very, very polar. And it can literally dissolve everything. It really can. It may take time, but it varies. Some of the stuff is dissolved right away. Some of it could take some time. But water will dissolve literally everything. Okay. Water has very strong hydrogen bridging forces between the molecules, and therefore is very polar, has high IMF, has very low vapor pressure. Boiling point is relatively high at 100 degrees Celsius. Its melting point is 0 degrees, has high surface tension. And something unique about water is that it expands when it freezes, and therefore its density changes, becomes less than 1, and therefore ice floats because of the expansion. Very unique in the crystalline structure. I'm told that snowflakes are all unique. I can't verify that, but that's what it is. It's interesting in the solid structure. In the lab, nature tends to pick the 6-member hexagonal shape. It's found a lot in nature. Interesting. All right, let's talk about heating curves. We're almost done with this chapter here. Okay, what we're doing here is we're normally we could do this in the lab. You can demonstrate this. So we take a material which is a solid, and we start noting the temperature, and then we add heat to the system, and we periodically check the temperature. The result is that we create this graph. Now, on the slope of this graph, as we start off in the solid, the first slope is all. Let me mark these. The slope here, all solid material. Okay, at every slope we have solid material. The next slope, we got liquid material, and then eventually we got another slope where we get all gas. Notice something interesting. We get a plateau, two plateaus. Okay, the first plateau, and this pertains to a lot of the material chemicals out there, but this could easily be water, for example, and this could be an ice cube. We reach a plateau so that no matter how much heat we put in there, the temperature remains the same. And in here, we have a mixture of solid and liquid on that plateau. Okay. And what's happening here, the reason there's no increase in temperature is all the energy that you put into the system is breaking up that interaction, the IMF interaction. You're breaking up all that solid to convert it to a liquid to get it up to the next phase. So eventually, when you have added sufficient amount of energy and all of that solid has been converted to liquid, then you get another rapid temperature increase. And then you have another plateau. And then here, again, you have a plateau where you have a mixture of liquid and gas. Again, you have a plateau where all the energy you put into the system is being utilized to break up the IMF interaction to convert that solid, that liquid, into the next phase, which is gas phase. Okay. And that's what's happening there. Here we go here. So this could be typical water, where we have ice going to liquid to gas. And here shows our plateau. So thing to take away from this, especially if you like to cook and save energy, when you hit that plateau right there, you're boiling water, you don't have to, no matter how, turning that heat up is not going to increase your temperature. As long as you got water in there, liquid in there, you're not going to get a higher temperature. Water is going to boil at 100 degrees no matter what you do, okay? Unless you put in there a pressure system, but we're not doing that. So, and it's gonna mount at 0 degrees. Okay, so save your energy. You're trying to boil some spaghetti. You think you're gonna kick up the temperature. If it's boiling, then that's as high you're gonna get. That's 100 degrees. All right. So be able to identify where the solid area. Be able to identify where you get a change of phase. Liquid to solid. Here's a liquid phase right here. We got the change of phase of liquid to gas, and then all the way all gas right there. So that's basically what we're going to take away from that, is that we have two plateaus and all of that energy is being utilized to break up the intermolecular forces of that liquid or that compound, whatever that may be, breaking it up. Okay. Now, think about this. This is true. We're going from left to right, but we can take gas and bring it back into the liquid and vice versa, go the other direction. And what we're doing is we're taking away energy. As we put energy into the system, the molecules become more energized, right? So they go from a solid to the liquid. The liquid has more energy than the solid, and then that liquid goes to the gas. The gas molecules have a lot more energy. If you take away those energy away by cooling them down, they come back down, and then the intermolecular forces start picking up and then become the new phase, and they start interacting with each other, and we keep taking the temperature out till we bring it back all the way down to the solid. Okay. If ice sunk, it would be a little different. Yes, it would. In fact, you can get ice if you take an isotope of hydrogen, for example, you got hydrogen 1, 2, and 3. If you take ice crystals of hydrogen 2 and 3, they sink All right, so let's continue. So basically, in a nutshell, during the phase changes, the temperature remains constant. All of the energy goes into breaking up the IMF interactions. It's not breaking up any bonds. We're not, there's not that much energy. You know, the bond energy is up here. The IMF forces are like below my floor level. Okay, there's a big difference in the energy requirements. All right, so we're just breaking up the interactions. You're not breaking bonds. Remember that. All right. That being said, congratulations, guys. End of chapter 14. All right. On Thursday, we would do chapter 15, which is very, very short. But deals with solutions. Now, it would probably take us a few minutes to knock it out. So I'm suspecting that on Thursday, I'll finish up 15. If there are not any questions about these chapters, and then I'll jump into the gas one and then finish it up on Tuesday if we don't get it all done. All right. Yes, got her. Yes, exactly. Heavy water. And it was real big in World War II when you were trying to find it for the atomic bomb. Heavy water. All right. So, got here.